Hello, everyone. Today we're going to start working on stack frame and or stack frames. So this is exactly what we started it last week, and I hope by now you guys know what stack parameters are and how passing arguments in terms of using registers and in terms of using local variables. And I hope that now you understand how the stack grows and shrank, okay, in terms of pushing and popping things out of the stack. And I hope that it's clear right now that you know how the stack pointer works. Every time we push, we decrement first, and then we assign the value. And if we pop, we copy, and then we increment by 4. So we either decrement or increment. And I hope that now you understand, by now you understand what cleaning a stack means. Okay, so cleaning a stack of the stack pointer is pointing at a return address. That is the right time to say return, because return believes that the stack pointer is at the return address. If that is not the case, then we have to clean up the stack. And clean up the stack means either we add 4, add 8, whatever the number is, to get the stack pointer pointing at the return address. And we learned that we can do that by adding value or subtracting. It depends on where the stack pointer is to the ASP with the amount. Okay, so this could be any number, 4, 8, or whatever. It depends on where the stack pointer is. Or we also learned that we can do it using the return. So this is what we call the C convention, and this is the standard convention. Okay, so the C convention we add, in here we just say the amount, right? 4, 8, or whatever you want to return these stack pointers to point at. So the only thing when you use the return, hopefully you understood that when you say return and you provide the value, so when you say return, the cleanup is going to happen at the callee side. So when you go back to the caller now has everything in place. If you use the C convention, and that is mainly is going to be when you are at the caller side, you need to clean up the stack before you make the next move. Okay. So today we're going to continue, but we're going to focus on how to reference if we have a value or we have a variable assigned into a frame. So this is the caller or the callee frame, and this is the caller frame, right? That is the caller and that's the callee. So what if I need to reference to a parameter? What we going to do? Okay. So if you look at the case right here, if this is your array, because this is usually a reference parameter, if you have a reference parameter or group of parameters that you need to access, and you are in the callee side, so you know that you have the base pointer, and you know that since they are parameters passed by reference, then they are in the caller side already, right? If they are in the caller side, then you are moving in the right here in the direction of the memory, right? So you are moving in this direction. So if you're moving in the memory direction, then you're just going to say the base pointer plus the amount. If you want to access this one is going to be 12, because this is going to be 4, 8, 12, right? And if it's going to be something, it goes against the direction of the memory, then you just need to subtract. All right. So here, if we want to move to ESI, we're just going to say we don't have the offset, but we have the address already pushed inside the stack. So we're just going to say base pointer plus what? Plus 12. That means we need the offset. We assign that to ESI, and then you can start your coding from there. Okay, you can start coding from there. But this is the way you access a parameter in the stack. Okay, and then this is the other part right here, which is the reference parameters. So this is another way. If you look at this example, like this is the whole example right here. You push the offset into the array, and you push the count, and then you call the array fill. Okay, so when you say call the array fill, then you're going to push the address of the next instruction, whatever the instruction that comes right here. You're going to push it into the stack, and then you're going to move to the callee. Right? So the callee is going to be what? The array fill. So if we're going to go and look at the array fill right here, this is what you have in the array fill. So in the array field, the first thing you're going to push the base pointer. So the base pointer value. So base pointer before here, before it was pointing somewhere in here. But what we did right now, we said, okay, your value that was allowing you to point at this part, save that value in the base pointer in this space. And then now we're gonna move the stack pointer to the base pointer. So the stack pointer is pointing here. And since now we're gonna update the base pointer with the stack pointer, then the base pointer now is gonna go and point right here. And that's the old value. So now we have the base pointer and the stack pointer is pointing at the same thing. And you know what this instruction is going to save all general purpose registers. And then right now we're just going to say the base pointer plus 12. If this is my base pointer, because it used to point somewhere in here, now we brought it right there. So if it is right here, we're going to say base pointer plus 12, then we need to access the offset. So we move the offset to ESI right here. And then we need the count because we want to do a loop, right? So we're going to say the base pointer plus 8. Why plus 8? Because we want to access the beginning of this count, right? So you're going to say plus 8, you move it to ECX. That's the way we access parameters. And then we're going to compare ECX with 0. Of course, ECX has a count. It could be 3 elements or 4 elements, whatever the number of elements you have in the list. All right, so you compare it to a 0. If it's equal, then you jump to the L2, that means you're out, you have nothing to do, okay? The count is 0, there is nothing, there are no elements in the list. And then if that is the case, you just pop everything back, general purpose registers, and then you need to pop the base pointer. So you copy the value right here to the base pointer. So the base pointer is gonna go and point at whatever it was pointing at before. And if that is the case, then now what we're going to do, then next we're just going to say what? So if we do this a pop, we copy, and then the stack pointer is going to point right here, right? And then right now we're going to say what? Return 8. So return 8 means what? We're going to go back to the caller, okay? And then we're going to add what? We're going to add 8. So if we're going to add 8, we're going to point whatever. So the stack pointer is going to go from here. And then it is going to point at the first 4 byte that they comes after this, these 8 bytes, the ones that we have right here. And then we are out. But if the list has specific elements in there, then that's easy. Then we are not going to go there. What we're going to do, we're going to move 10,000. That's a random number. Okay, let's say you want to select a number. You want to fill up an array with certain elements, right? So let's say you want to fill in the array with any number between 0 and 10,000. Just assign to EAX at 10,000, and then you call this function random range. So this random range is going to select out of this range a number. Let's say 5. Okay, and then once it do this, then it's going to move the AX to what? To ESI. Do you see it? This is indirect access. That's why it's in square brackets, because that is what? That's the offset that points at an array. And it seems the array that we are pointing at is of a size what? Of a size word. Okay, we move that one, and then we're going to increment the ESI. So if this is the element that the ESI is pointing at, if you have a list right here, and this is the element, now we need to increment it to point right here. So let's say here we have the 5. Now we're going to fill the next part. Okay, then we're going to loop back. When we're going to say loop back, we're going to go back to L1, and then we're going to move the 10,000 again to EAX, and we select another number. Let's say it's going to be 100. Okay, so we're going to take that 100. We're going to store the 100 right here, right? And then after that, we're going to increment. So we're going to increment the indirect access pointer to the next point, and then we're going to loop until everything is going to be fine. Once everything is going to be filled up, once we did what we are supposed to do, we're just going to say pop, and then we just repeat what I explained right now when we exit the loop. All right, so this is basically the idea of accessing. So try not to let those details get you out of the main topic. I believe that you understand all of these details that we have in here, indirect and the loop and everything. But the focus is really right here, is how to access the elements in a stack. Okay, so that is basically the stack frame. All right, so from here to there, this is everything you need to know. So if you have any issue with those, Just try to look at the slide, watch the video, and if you still have doubts, we have office hours every Monday and every Wednesday, right? So just come during those office hours for each section. Monday, Wednesday, you have 4 to 5, and then Tuesday, Thursday, you have 5 to 6. Just please stop by, and I will try my best to help. All right? So if that is clear, then now you are ready to go to the recursion. Remember, if you have any doubt in here, the recursion example is going to just shows that to you, that you are missing something. Okay, so recursion assumes that you know the stack. I don't care much about the recursion because I know you guys know what the recursion is and why the recursion and when to use the recursion. This is all things that being taught in Introduction to Computing or Programming 2 and in data structures. So you know what a recursion is, right? So this is something that you know, it's a techniques that is used to solve specific problems, okay? When a function calls itself, like when you solve a problem like a factorial problem, right? When you solve a factorial problem, instead of writing multiple copy of the same function, you're just gonna store the value and a specific value, and the function needs to call itself. And if you might forgot, I would just remind you that the reason why a stack was created is because of the recursion. Because they know if they need to solve a recursion problem, they need a stack, okay? And then they need the function to call itself. So these are one of the main reasons. So remember when I said there is only one language that doesn't really have or doesn't really use recursion, which is Fortran. So how Fortran is going to go about recursion, because Fortran is mainly known for the a language for finance, right? For mathematics and doing all the basic uh, um, basic arithmetics and I mean mathematical solutions. So they have their own technique. It's very weird, it's not common, but they have their own way. They don't use the stack. But the whole idea is we need the stack for a problem like a recursion. All right. So if I want to show you what the recursion is, just to remind you, like the basic idea, we have something we call endless recursion. Okay, so I think this should be clear to everyone that at least in Java or in a high-level language, that you know when the recursion is going to be infinite. It's going to run forever. You never find a solution, and that is because of one reason, right? It's you're not going to reach the end, right? Every time you subtract one, you subtract one, you subtract one, and it's going to go forever. Okay, so in this example, I'm just going to set up the scene. So here we have a main procedure right here, okay? And in this data, we just have a string. In this example, we say this recursion never stops. That's a string, okay? And this is the variable name. And here we are calling an endless function. So just imagine we have a stack right here, okay? All right, if we have this stack right here, and then let me say I have the stack pointer here, pointing at this part. So when you say call, we know call is going to be subtract because it's a push. So we subtract in here and we push the return address, right? And then the second thing, we're going to look at the instruction pointer, and the instruction pointer is going to go to where? Endless function. So this, instead of pointing at this address, now this instruction pointer is going to point as the first instruction. So that's where the instruction pointer is going to point. Right? So in the first instruction, what we're going to do, we're going to say the endless string, that is the string we have right here. We're going to copy the first address that points at the T, and we assign it to EDX. And then we're going to call what? Write string, right? So this recursion never stop, right? And then we're going to go what? Call endless. So when we're going to say call endless here, we're going to again subtract and then copy the return address to endless. This is to the main, right? So to the endless number one. Okay, forgive my my drawing skills. All right, so this is going to be the part in here. Okay, and it's going to go back and call itself. So again, it's going to move this, and then it's going to print the message, and then write the string, and then subtract, and then return address to the endless two. That's the second time. It's going to go again. So it's going to go like this forever. Do you know why? Because we never have the opportunity to run return. because that's when we're going to return, right? So it just, the function is going to call itself. It's a circle. Okay, so that's a loop. Call. So it's going to stack pointer, return address, and then return address, and then it's going to go like this until you exhaust the entire space of the stack, and that's when the program crash. Okay, your program crashes because it says you are running out of space. So the stack has a space, remember that? So every stack, at least the default value, we're gonna have the 4,000, maybe a 96, right? If you remember that. So it's gonna, if it exceeds this number plus one, so it's gonna be 97, then the program is gonna crash. Say you exceeded your space, you're moving somewhere else. Okay, so this is just a basic idea of how the recursion works, but this is not our point, just to show you like what is an endless recursion. But the whole idea when we talk about the recursion is to solve a factorial problem, right? So if you want to understand that, and I assume that you already know that, right? So if you already know this, then you know if we say what is factorial of 5, right? So the factorial of 5 right here, you know you're going to compare it with a 0. You return 1 if it's a 0 because we don't have the ability to compute it. If it's 0 or less, we're just going to return 1 and we're going to get back. Else, we're going to just multiply 5, right, by factorial, which is 5 minus 1. Okay, so it's going to be 4 factorial, right? So this is what's going to happen. So what is 4 factorial? We don't know. Then the function is going to say, call yourself. And then it's going to go back and try to say, okay, what is 4 factorial? Then we're going to say, oh, it's easy, 4 by 3 factorial. Again, we have the same problem, was 3 factorial, right? Then we're going to say it's 3 by 2. We don't know 2. We're going to go, oh, we find that it's 2 by 1, but we don't know 1. And then when we go back to the 1 factorial right here, we're just going to say 1 by 0. So we're going to say what's 0. And then now we say, oh, 1 factorial of 0 is 1. Once we find this, then we're going to go back and substitute. So right here, we're going to substitute factorial of 0 with 1, right? So we get a result. Then now we know factorial of what? Factorial of 1, right? So we're going to substitute it there, and then we get factorial of 2, and then we get factorial of 3. So we're going to go upward until we get the result, which is 120. You see what I'm talking about? So this is basically what it is. First, you keep asking the question until you get to the 0, and then you're going to go backward. This is what we call the base case. If you go to the base case, then now you're going to go back and you're going to solve the problem, right? But remember now, you are calling. Every time you say here, you are calling. So if you say this, then you need to think about the stack, okay? Because you need to remember who called what, right? So this is the ESB pointing right here. And if for the next time you call, that's the return address. That is the return address. So the stack grows, right? Until we get to the return address N, which is the 5, right? Once we get to the base right here, then we want to go back to this. And then we're going to go back to this and this and this until we get to the main, right? So how do we remember how the computer program remembers that, right? If needs, we need some stack. So that's the whole idea. So we're going to look at an example of a factorial that is really small. So that way you're going to see how the stack is going to be created, and how the stack later is going to, and how the return later is going to go back and free up those frames. So this is going to be very important. And if I were you, I will follow the example, and then I come up my own number with my own number. And then I will have a piece of paper and try to write my own code in a different number and try to trace whether that is the case. Okay? So I think you have been already introduced in the lab to the recursion. So I believe you are ready now. You need just to solidify, or you need to I need to emphasize the theory right here. All right. So right here, if we need to compute the factorial 3, right? So if it's 3, we know we need to figure out factorial of 2 and then factorial of 1, right? And then once we do this one, then we're going to have what? We're going to have the result, right? So we would like to see how that is going to be captured by the stack. All right. So let's look at this example right here. So first we're going to say what? Push. Push means that, keep that in mind all the time, please, guys, that the stack pointer was pointing somewhere in here. When we say push, we're going to decrement it right here. Okay? And then we're going to push 3. All right? And after that, we have what? Call. So call is going to push the address of the next instruction. That's the address of the next instruction. Okay? So the address of the next instruction is going to be pushed. So that means we're going to decrement the stack pointer. So the stack pointer points right here now. Okay? And then now we know that the call is going to also change the instruction pointer, right? So that's going to be the instruction pointer. So the instruction pointer needs to go to this function. Okay, and I assume right here, if you see the base pointer, that the first instruction in this function is to push the base pointer into the stack. Okay, so let's go now and see what is going on in terms of the second frame. So yes, the first thing in the factorial function that we have right here, the first instruction we have is going to say push the base pointer. So the base pointer now, the value, so the base pointer used to point somewhere, I don't know. Okay, so the base pointer is pointing somewhere in here. So we said, okay, the value you have, let's say if it's 12, that points at a specific location in here, we're going to save this 12 right here. And then now we are moving what? The stack pointer value to the base pointer. So the base pointer now is no longer pointing right here, is going to come and point at where the stack is. Okay, so this is my base pointer. So that is the fixed reference. If I have the fixed reference right here, so now that's accessing the memory, accessing a parameter in the stack frame. So we're going to say the base pointer plus 8, that means we need to access 3. Okay, so we assign this to where? To EAX. And then now we are comparing EAX, which is 3, with 0. We say jump if it's above. Is 3 above 0? Yes. If it is, then we need to go to L1. That is L1. Okay? So when we come to the L1, we're going to decrement EAX. So EAX is 3 minus 1, then it's going to be what? It's going to be 2. Okay, guys? So we get it at 2, then we push. So when we push, we're going to decrement first, right? So when we push right here, we are right there. We're going to decrement the stack pointer, okay? And then we're going to push 2, okay? And then after we do the push right here, that's where the stack pointer is. And then we say call factorial. So we are recursive now. So call means we're going to what? We're going to push the address of the next instruction. Keep that in mind. That's the next instruction. This is comment, not an instruction, comments. And this is just a label. So this address of this instruction is going to be pushed. So that means what? We're going to decrement, and then we're going to push the address of the next instruction, which is this address, right? So we call factorial, this address is going to be pushed. And we're going to go back to the factorial function, which is the beginning, right? So in the beginning, we're going to do what? We're going to say push the base pointer. So when we say push again, we decrement the stack pointer here, and we push the base pointer. Okay? And then what we did in here, we say move the ASB to the base pointer. So the base pointer no longer pointing right there, right? So we bring this base pointer, and now it points right here. Okay? So the base pointer now points right here. And then now we say the base pointer plus 8. So the base pointer plus 8 is going to be what? It's going to be 2. Okay? And then we're going to compare what? Is 2 greater than 0? Yes. Then we're going to go for the second time to the L. And that's what you're going to see in the next slide. So if we're going to go to the L1, we're going to decrement, right? So we're going to decrement what? We have 2 in EAX minus 1. Then we're going to have a 1, right? So if we have a 1, then we know that what we have in here is the stack pointer, right? So we're going to say decrement because we want to push, and then we're going to push the 1. You with me? So we push the 1, and then we're going to say what? Call, right? Call factorial. So the stack pointer again in here is going to be called as a push, is going to be decremented, and then we're going to have the address, the return address, right? And then again, when we do this, we're going to go back right here, right? So that's when we're going to say push again. That means what? Decrement. So then we're going to say push the base pointer. So the base pointer that points here, the value is going to be assigned. And then we're going to move the value of the stack pointer, right? The stack pointer to the base pointer. So the base pointer and the stack pointer are pointing right here. Okay? And then now we're going to say base pointer plus 8. Base pointer plus 8 is going to be what? Is going to be a 1 now. Is 1 greater than 0? Yes, then we're going to go right here. Okay? And this is what we're going to see. Okay, so if we're going to go back right here, then we have 1 in EAX, right? So we're just going to say 1 minus 1, it's going to be what? A 0. And then we're going to say push. So since it was pointing right here, we're going to decrement it, the stack pointer again, and then we're going to push 0. Okay? And then once we do this, we're going to say the call. So the call again is going to decrement first, and then it's going to push the address of the next instruction, right? So that's going to be decrementing, and then it's going to go back to where? It is going to go back to call itself. So this is push again. So the push is going to say decrement and push the base pointer, right? And then when we are right here, we're going to say now move the stack pointer so to the base pointer. So the base pointer now is going to go back and point right here. All right? And then now we're just going to say the base pointer plus 8. So this is my base pointer, and plus 8, we're going to go to the 0. So EAX has a 0. Okay? So if that is the case, now jump if it's above. So is 0 above 0? No. So we are not going to execute this instruction. We're going to go to the next instruction. So in the next instruction, what we're going to do, we're going to assign 1 to EAX, and then we're going to jump to where? We're going to jump to L2. And this is what we're going to see right here. So we're going to assign to EAX1, right? And then we're going to go to this instruction. When we go to this instruction, what's going to happen? So we are right here. That is the frame number 4. Okay? So when we are right here, we said what? Pop. So we're going to pop the value of base pointer back to the ESP. So the ESP is going to go and return pointing at this part now, because we pop this value and assign it to the base pointer. So the base pointer is going to go right there. Correct? And then what we did, so when we do the pop, we know first copy, and then what? Increment. Okay, and then now we are ready to say return, because that's the return address, right? So when we say return, we know we're going to return safely, but when we return, we have to do what? We have to add 4, right? So the stack pointer now is pointing right here, because that's what the return is going to do, and that's what the second plus 4 is going to do, right? You with me, guys? So now I know that the base pointer is pointing here, and when we return back, so the stack pointer and the base pointer, they're pointing at this value. Okay? So what we're going to say here, when we're going to say return, return means what? Pop the top of the stack and assign it to whom? And assign it to the instruction pointer. So the instruction pointer now is going to point here, because that's the return address. Remember, every time we assign this value. All right? So if we do this part, then we are right here. Okay, so if we are right here, let me just go back. If you are right here when you say return, this is the case. If you are right here, you're going to say what? Base pointer plus what? Base pointer plus 8, right? If you are at the base pointer plus 8, that is the base pointer plus 8, then you are right there. All right, so you move this value to where? To EBX. And you're going to say mul EBX. So EBX has a 1, I know. So mul works what? It's going to by default go to what? EAX, and EAX has a 1. So 1 by 1 is going to be 1, and this is going to be assigned to what? To EAX. And back, now we're going to go to what? To pop. Okay, so if we're going to go to pop, this is what the state is going to be right now. We're going to pop, we're going to return, and that means just repeat what we said right now. Okay, it's going to go to the next frame. So if it's going to go to the next frame, now it's going to say return. When it's going to say return, it's going to bring it back to this address, right? And in this address, now we're just going to say base pointer plus 8. So base pointer plus 8 is going to be 2 now, because we changed the base pointer. Okay? So if we do this one now, then we have an EBX, what, 2? And EAX already has 1, because we multiplied 1 by 1. Then now we're going to have a 2, and that's going to be the value of EAX, right? And then we're going to pop again. Okay, so when we're going to pop, we're going to assign the base pointer. So the base pointer is going to go here. And then after we do the pop, we're going to increment, and then the return is going to take this value, right, guys? And then again, after we do this one, is going to take it by 4. So that's later is going to, both of them, they're going to point at the base pointer, right? At the same space. And then this is what's going to happen here. So we're going to go to this part, and that's when we're going to say the base pointer plus 8. We're going to get to the 3. So EBX is 3. So now we know 3, and EAX has a 2. And then the result now is going to be what? It's going to be 6. Okay? So if that is the case now, we do the multiplication. Then we're going to do what? Again, we're going to do the pop. Then the base pointer is going to point, I don't know, at wherever it was pointing before. And then we're going to have the, after we do the pop, it's going to come right here, right, guys? And then when the return is going to do the return, right? The return is nothing but a pop, right? So when it do the pop, from there, that's the return. It's going to bring it here by 4. And it has to add another 4. So the stack pointer and the base pointer, they're going to point at the same point. Okay, remember this return has 2 pop, right? The first return is going to pop the address, and then the first return, which is the STD call convention, is going to add another 4 to clean up the stack. Okay, so if that's the case, then we already reached to the point to return when? To return where? To the main, because that is the return address to the main function. So that's when we have to go back to the main function, and if we go back to the main function, the program is going to continue from there. All right. So this is the whole idea of the stack, okay, and using the recursion. So you just started with a simple thing in here, 1 frame, and then you push 3. Stack pointer was somewhere. You push is going to decrement and push the 3 right here, and you call the factorial. Then it's going to decrement and is going to have the return address to main. Okay, and then when you go to the coolee in there, so the coolee first push the base pointer, right? And that means we have to decrement, right? And then it push after it decrement the value, it's 2 in here, right? And then it calls itself return address. So it's gonna keep decrementing. Okay? And then once we go and return, we know when we return, we're gonna go to the beginning. So that means decrement. And we have a base pointer, okay, and the stack pointer and the base pointer, they're pointing at the same place. We decrement 2, so it's going to be 1, right? And that is when we're going to go where? We're going to go back. When we're going to go back, that means the return address, okay? And we're going to go back to the return address, and then we start doing it again. It's going to be the base pointer is going to be pushed, and the stack pointer is going to be pointing right here, and the base pointer also is going to be pointing right here, okay? Until we get to the last one, when we're going to say, okay, we get to the base pointer right here, we subtract 1 from 1, we're going to push the 0, and then that's going to be our return address, okay? And then we're going to go back. That's when we're going to get the base pointer. This is very important, guys, okay? When we're going to get to this base pointer, and we assign the stack pointer to the base pointer, but when we do the comparison, we are no longer calling any other function, right? Because that's the 0 we have to return. So you need to know that you have this 4 bytes extra. So if I ask you to compute the space, it's going to be whatever you have here plus this 4. You see it? Because that's not needed, but we had to do it because we have no way to know whether that is the last call or not. So this is a very detailed thing that you don't know unless you actually look into the stack. I mean, look at the stack and see what's into or what's being inserted into the stack. So that way you know that you will have a 4 bytes always going to be wasted, because that is when the stack thinks, because it's a machine, it thinks, okay, there could be another call, but at this point we compare 0 with 0, and that's when we're going to say jump if it's equal. So it's not, if it's not equal to, it's not greater than 0. If it's above, I'm sorry, if it's above 0, so it's not above 0. So that's why that's why we are not going to return to call the function again. So it's going to be all return. So this is going to be an extra space. Okay, guys, kind of clear? So what all it takes, guys, just take a factorial, okay, of 2, okay, factorial 2, and try to write the stack. Try to draw the stack. Okay, just follow whatever we have right here, whatever we covered right here. Start from the beginning and draw this. Try not to look at the slides and start from here. That's your main function. So push 2 in there and then call the function. So here you're going to have a 2, and then you're going to go back to the return address, and you're going to go to the factorial function. That's when you have the base pointer and you do the decrementation, and then you call the function itself. So at least you're going to have 2 frames in there. That's very small. So that way you're going to have a sense of what we are doing. Instead of 3, do it just for 2. Because you're going to just say 2, and 2 is above when you go right here, right? We're going to go with the 2, right? And then we access the 2 right here. And then we compare. So it's not above. So we're going to go right here. We decrement from 2, 1. And then that's when we're going to create the second frame, right? And we call the function. And then right now you're going to access the 1, and it's not above. And then you're going to come here, and then that's when you're going to get a 0. So if you do it this way, you hopefully going to get those frames. Okay, let me go back to the slides that I have at the end. So you're going to have for 2 right here, you're going to have the first frame when it was 2, and then the second frame when somewhere in here it was 1, and then the third frame somewhere in here when it was 0. When it's 0, you have to stop right there. But remember, you're always going to have this extra base pointer thing in here. And that's a flaw, to be honest, a design flaw. Okay, and I can manipulate the situation if I want. Okay, but that shows you knowing the low-level details. They're going to help you in terms of space, performance, security, whatever you have in mind in terms of software quality. Okay, so hopefully this is makes sense right now. But if it doesn't, then that shows you still need to do a lot of work. You need to really understand everything I explained from chapter 5 to chapter 8. That's very important. They have to come together. Okay. So if that's clear, then we're just gonna cover 2 basic topics in here, and then we're gonna move on into the real numbers, because we had enough with the integers. It took us so long. I mean, it took us a long time to understand the integers, right? So now we need to know more about the floating points. But before we go there, I just want to bring your attention to 2 basic ideas, which is parameters classification. You have input parameters. That means you pass the data as if you pass a value in there. You don't need to change anything. Or you might sometimes you call a parameters as an output. So you're passing the output right there, and the output is going to be is just going to be returned. So you have a reference, so you are passing a pointer. Unlike this, when you are passing the data, you're passing the pointer. But when you pass the pointer right here, all you're trying to do is to assign a value. Let's say if that is your pointer, and then you do some computation and you assign 5. So you're not receiving, okay? And this is the third part, which is input output. So I might send you a parameter as an input, which is 5. You use it in your computations, and you maybe change it, okay? And you return a different value. So this is what we call input output parameters. And I think these are the tools that you guys are dealing with when you pass with the reference. So if you're just passing an object, and if that object's just being used to do some computations in there, okay, so that's the input output. But if just it's being used, sent into there, so that way you're going to change the value, so that's going to be the output. So your return value is going to be the output. So I assume that these things are already clear, especially if you know parameters in a high-level language. And there are some basic troubleshooting in here, and just trying to bring your attention to the book. So try to look at the book. You'll find a lot of examples in troubleshooting. If you have problem dealing with the stack, hopefully, or procedures, they're going to help you a lot. Troubleshooting number 1 in here, if you save, restore register. So you have to keep this in mind, okay? Save and restore. If you save registers before you jump into the callee, make sure that when you return from the callee, you're going to restore them. So this is a common mistake that programmers make, okay? And maybe when you need to use the invoke, or maybe when you need to pass an immediate value. So when you pass an immediate value, that is very important. So when you pass an immediate value, guys, it's dereferencing its address will likely cause a general problem. So try not to pass an immediate value. If you have an immediate value, just keep it in that function. I know you guys maybe have already had an idea about those things when you learn Java, okay? And if you use the invoke, this is unique. When you use invoke, that means like call, okay? So there is another way to call a function. You just say invoke, and that is very unique. So when you say invoke, for example, and you pass a D-word argument using the PTR, so the MASM has no idea whether what you're pointing at is a byte or 4 or 2. So you have to be careful when you pass things using pointers. The meaning or the semantic depends on you, not the MASM. MASM just see an address that points at a byte. Do you mean this byte and the next, this byte and the next 3, this byte and the next 8? MASM has no idea. It's all us. So if you don't have that in mind, a lot of things could happen. Okay? So these are, and others in the book, they can you can add to your knowledge when you write procedures, okay? So these are very important. There are more details in terms of what's invoke, what's an address, what's a proc, what's a proto, but I don't really have time for those because I want to move to the real numbers. So if you have time and you want to look at those in the book, that's going to be great. If you have time, you can also look at the slides. I have detailed slides, I mean, simple detailed slide in here. So they're just going to introduce you into what those directives are. Because what mattered to me is that now you understand what a stack is, the relationship between a stack and a function, and how a stack is controlled by base pointer and stack by the stack pointer and base pointer, and how the base pointer helps in creating frames, and how the frames actually being created, and how variables or parameters stored inside the stack are being referenced. Okay, so hopefully this is clear in your mind. If you have those 50% of those knowledge, that's going to be great because to be honest, it takes time to understand the entire stack. It takes you a couple of years. And if I were you, I would visit the stack every once in a while. Every time you add a year or a six month of programming experience, get back into the stack and try to play with it. Because I mean, I'm not saying that's going to help you solve like real life problems. It's just going to make you a better programmer in terms of understanding. You know how a program works, and you know how to debug if something wrong happens. Okay, so I will stop right here for this part. I mean, for the procedures, and then I'll try to go and move to the next topic. Okay. If you have questions, as I said, guys, I have office hours today, and these office hours, they're gonna start at 4 and 5. It depends on your section. So please refer to the announcement at iCollege. Okay. So let me see. This is gonna be our chapter. Okay. So let me see first. Where is that? Okay, so I need maybe to go here, and that's chapter 12. So let me go to the resume sharing and new share, and let me go to this part, and I hope you guys see it now. Okay, so I'm just going to introduce you. I promise I'm not going to push you too hard, so you're already dizzy by just looking at those slides, but hopefully now the stack is very clear. So so far we've been handling integers, right? So this is what we have been doing so far. Let me go back and choose the pen. So what we have been doing is mainly the integers. So now we know quite a lot about the integer, right? We know its range, right? We know its size, right? And then we know the flags, and then that's when something goes wrong, okay? And then we know how to do arithmetic to them, right? And then we also learn how to do how to check for the size, how to check for the range, how to, if we exceeded the range or the size, how the flags are going to capture that, and how to do basic arithmetic. And then when we do the basic arithmetic, the computations, and here, how the E flag is really watching whether the result is 0, overflow, carry, or it depends on whether the integer is signed or unsigned. and how to move them as well. So we move with the move ZX, and we also learned move SX. So these are all things that we learn in integers, okay? So remember when we go to Java or C and you say integer A equal to 5, just keep that in mind, that you know that this is a data type. It's not only a data type, but decide the range or the size is 32-bit, and you know the range is going to be half because this is what sign integer. So it's going to be 2 billion, okay, for the positive and 2 billion for the negative. So you should know this when you go to Java. And you know, right, if you exceeded the range for some reason, that the E flag is going to really capture that. So this is all about the integers. So if you look at the CPU in this way, guys, so that is the CPU. The CPU has two units, integer units and floating point units. So we already covered the integer unit kind of now, and then we're going to focus on the floating point. So you will see the support of the hardware when it comes to the floating and the integer points. Okay, so that's a floating point. So let's look at the whole story, right? So if we look at the integers, and if I give you a number, let's say 5, we know it's easy, right? We just convert the number into binary, right? 1 0 1 0, right? 0 0 0 0. So I know this is the standard storage capacity, and that's a byte. And then now I know I will store this number if it is unsigned. If it is a signed number, we know that this is a 2's complement. If it's negative, we're going to change this bit and everything. Now we're going to see whether that is the case in when it comes to the floating point or real numbers. So it's going to be mainly, we're going to focus on binary representation, floating point binary representation. Is it going to be something like the integer right here, or is it going to be something else? Okay. So once we do this, then we're going to understand how to identify floating points, and then how to use some basic arithmetic floating points instructions, which is completely different. It's a completely different CPU. You will see this on this week's lab. Okay, you're going to play with it. So let me just take you through the big picture right here. So programming languages in general, they support the fractions, which is the floating point. They call them a floating point, right? And these are examples, right? So if a language supported, then there must be a hardware. Because without the hardware, now I think you know after your integer journey that you know nothing is gonna exist without the support of the hardware, right? So if we have a number like this, how are we gonna store it in terms of binary? I know that you've been introduced to this in Introduction to Computing, how to represent fractions into binary. So this is important for you to go back and revise the material. These are prior knowledge, and it's very much important, okay? But I try to do my best to remind you of those basic knowledge right here. So if we want to represent this number, then we have multiple formats, right, guys, to represent a fraction or a real number. One known way is the scientific form. So if you can put a number in the scientific form, then okay, we have a way to design a hardware. If you can do this, then with the scientific, we can kind of design a hardware that can store a number. Okay, so if this is your fraction, if you convert it into this, then we're gonna put it in a specific format. But do we know the scientific form can come in different forms? So we need specific forms that's gonna help us be very consistent, okay? So if that is the case, then we have to choose a system, okay, a one form of the scientific forms, and we're gonna start from there, okay? So this is what we call the normal scientific form notation, okay, or the normalized, right? So if you talk about this number, it only has one digit right here, right, guys? So this is what we mean by the normal scientific notation. All right, so this is going to be the number, and this is going to be the exponent, and this is going to be the base. Right, guys? You with me? So this is what we have for decimal numbers. So you're going to have only one digit. If you have 25.5, then you have to move this right here. You have to make it one digit. So it's going to be 2.55. So that way it's going to be in the normal scientific notation. And then you're going to have 5 right here is going to be the fraction. So this is 2 point, this is 5 the fraction. And then you have to tell me, since you moved this to this part, your base system right here is 10. And your exponent here, exponent 1 or 2 or so on. So if we move this one, this is just going to be to the power 1. We just moved it once. Okay, for this particular example. All right, so if you see 13 right here, that shows you that the number was being moved 13 times to make it just one digit or whatever. This is -9. That shows you that the points 5, 6, 3, 2, 5, 1, 2, it was here. So it has to be moved to somewhere else, right? So that way it's going to go to the right direction, or it's going to go to the left direction. It's going to go to the left, or it's going to go to the right. Okay, so that's going to decide the sign of the exponent. All right, so this form is very important. We need to know it. But again, we need to represent floating point numbers in terms of what? Okay, in terms of binary. So this is just to explain the idea, right? So this is in the right form. This number is not in the right form, right? So we have to move this point here, 1, 2, right? So it has to be in the right form. If we do it, then it's going to be the number. This is your decimal. This is the fraction. And this is the base, right? So you're going to say 2 to the power 2 because we moved it twice. Okay, if you want to move it to the right, then it's going to be minus, right? So I assume that you already know that part, right? Okay. So this is exactly what I mean by this number. So if you have zeros in here and you want to move this part, okay, you want to make this number normalized, then you have to move what? You have to move the 0 right here because this is not significant. This digit has to be significant, any number but 0. Okay? So if that is the case, then we just move this dot, the floating point. That's what the whole name comes from, the floating point. We're going to move the floating point right here. So that way it's going to be 10 to the power what? Minus 1. Okay? So that's the fundamental thing. But now I think you're very excited. How can we design a hardware that captures those factors? Because we have whole number, you have a fraction, we have a base, and we have exponents. So just now I'm preparing you of how can we do this in a byte, right? If you give me 8-bit, right? You have 8 bits. How can you store all of this in a byte? That's very interesting, okay? So how about this number? I will let you play with this number. So is it going to be positive or negative, the exponent? Is the exponent going to be positive or negative, okay? So you know the answer, I think, already. So play with it, please. Normalize it. So the focus is in the binary. So we need to understand, again, it's the binary number. Okay, the good thing about the binary number, we only have 2 digits, right? 0 and 1. And decimal, we have 0, 1, 2, right? 3 to the 9, right? So these are the digits. So this is not considered. So anything but 0. So in binary, if we do not consider insignificant, so we only have 1 digit, always going to be 1 because it's binary. 0 is not going to be considered. That's going to help hardware designers to use this to improve their storage ability, okay? Or to improve a lot of things, not only the storage. And then the same, we're going to have the fractions, and then we're going to have the base. So the base is 2, plus or minus. Remember, this is in base what? In base 2. So keep that in mind, okay? So I will show you the confusion just in a minute. So if you look at this example right here and the real numbers, is this number normalized? Of course, no. It has to be in the norm form, right? So we're just going to move the floating point 1, 2. Okay? So if we move it, this is exactly now correct. So this does not mean 10 in decimal. This means what? 2 in decimal. Because this is 1, 2, 4, 8, right? And this is 0, 1, 0, 0. Just imagine this is 2 because the base is what right here? Is binary. So try not to confuse yourself. If you see it 2 to the power 11, that's not 11. That's 2 to the power 3. Keep that in mind, okay, please? All right. So in the final or in the quiz, and if you want to say, okay, I want to do this in decimal, I'm confused. I want to do it 2 in decimal, I'm okay. Just tell me 2 to the power 2 in decimal. So that way I know you are confused a little bit about writing them in binary, though you shouldn't. Okay? So the question is, if we know this number now in binary, how can we store this number into a computer hardware? Okay? So this is one question. And then if we store it, then how can we retrieve it back and print it out? Okay, so this is gonna require a system. Okay, so how to store this number right here? So I came up with my own machine. I created an unrealistic machine because there is no way that you can do floating point with 8 bits. The reason I did this, so I'm gonna make just things a little bit easier for you to think about. Because if I go right away with the book, these knowledge are not available in the book. If I go to the way the book goes, then it's gonna be a little bit complicated, okay? So I will try to simplify this. Is this in the norm form? Yes, so this is gonna be the number. So we're gonna store, if we give me a byte, 8-bit, I will take the first bit for the sign, and then I will take 3 bits to store the exponent, and then I will take 4 bits to store the fraction. You see what I'm talking about, guys? So this is the sign, and this is gonna be the fraction, and this is gonna be the exponent. I think I already have the labels there. Okay, this is the sign, the exponents, and the fraction. And remember, if you give me 3 bits for the exponent, then again, we're gonna have a range. Okay, we're gonna be controlled by the range. So if I say 2 to the power 3, it's gonna be what? 8, right? All right. So remember, when you are using a fractions, the fraction 0.1 or negative 0.1. So we have maybe negative 0.0, maybe positive 0.0. So keep in mind that we might have positive 0 or negative 0. Do you see the table right here? Okay, and if we have infinity, it's also available. We have maybe positive infinity and negative infinity. And there is another case that we don't have a number. All right, so if you have a space that you can represent a number within a range 2 to the power 3, you have to keep in mind that you need 3 numbers or 3 parents that they're going to represent. One that represent positive or negative 0, one that represents negative or positive infinity, and one that's going to represent not a number. So if this is the case, then I only can do -2 to -3. So if you count them in your hand, you have them, or in the board right here, let me see, -2, -1, 0, 1, 2, 3. So this is how many digits? 1, 2, 3, 4, 5, 6, but we should do 8, right? So the other 2 digits or 2 parents are left for what? Are left for positive or negative infinity. This is one parent, okay, one parent. And positive or negative, sorry, or not a number. We have 2 types of not a number. So this is one parent. So if you add these 2 with the 6 that you have right here, okay, then the 6 that you have like here, 6 parents, okay? If you add this with this, the 6 with the 2, then you actually have an 8. Okay, so with this one, you can do just -2 to 3. If you have 4 or -3, then it is, you are out of range. That number cannot be represented by a byte. Do you see what I'm talking about, guys? Okay, so if the maximum number right here is 3, then we're gonna use this number as our what? We call it actual exponent. Okay, why we need the actual exponents? Because we need to add it to whatever the exponent is, and then that way we're gonna get something we call the bias exponent. I will explain that in a minute. But please try not to confuse this 3 bits with this 3. No, we are not adding the number of digits, we are adding the maximum number. I will show you this when we're gonna go to the real computers. It's not my own computer when I created a byte, and I tried to imagine things from here, okay? So if this is the case, then let's play with this number. How to store this number? Is this number in a normalized form? It is not, right? So we have to normalize it. That's the first thing, because the first digit must be significant. 0 is not significant. So we have to normalize the number first. Okay, so if we want to do this, this is now normalized. So we move this right here, this floating point. So now we're going to have what? 1 multiplied by 2 to what? To the -1. Okay, so keep that in mind. Okay, so that's a -1. All right, guys, so this is in decimal, -1. You can write -1 in binary if you want. Okay, so this is the first thing we do, and then we don't store the 1 before the dot. So this one, we are not going to store it. Why? Because it's obvious, it's always 1. I don't care. You see it? So as a designer, you said, I'm not going to store it. I will keep it outside of the storage. But if anytime I do addition or arithmetic, or I need to convert the number back, I will always assume 1 is there. Okay, because it's one thing. You don't have multiple things. And then the fraction in this case is going to be what? Nothing but what? Zeros, right? And we know we only have 4 bits. If you look at the design that we have 1 here, 1 bit for the sign, and we have 3 bits for the exponents, and we have 3 bits in here, and we have 4 bits for the fraction. You with me, guys? Okay. So if that is the case, then now we have 4 zeros for the fractions, and we already know the sign of the number, right? It's going to be a positive in here. And now we know what the exponent is, right? So how to store the exponent? Okay, how to store the negative exponents. We know, right, if you go and you look at this node, do I have it here? Let me take you back to this node. Okay, so right here, remember, we add 3 to the actual exponent to produce what? The bias exponent. So we have -1 in this case, and then -1, sorry, -1. Okay, forget about it. We have -1, and then we need to add 3 to it, because that way we're going to get the bias exponent. And what we're going to store is the bias exponent. Okay, so this is a little bit different from 2's complement, right? So in the integer, we're going to use the 2's complement. But right here, how to store the -1, 2's complement, it is not going to be something that we're going to use, okay? So we need something else. So that's what we call what? Use the biasing method. Okay, so in this case, in the biasing method right here, where n is the number of exponent bits, right? 2 to the power 3, and then that's going to be the number of the bits, right? And then giving the number of the bits, I can get the range, 2 to the power 3, it's going to be 8, and I know my maximum number, positive number, is going to be 3. So I'm going to use that number and add it to the -1, right? So if I say -1 plus 3, then I'm having 2. So this is what I need to store. Okay, so just add the 3. Then the convert it into binary and store it right away, right? So you're going to have the number right here is positive, then store 0 right here. And then this is your exponent. It's going to be, which is we call the bias exponent. We're going to store it right here. And this is going to be your fraction. Okay? So this is the basic idea. I'll give you a number. If it's not normalize it, normalize the number. And when you normalize it, you'll figure out the exponents. Once you figure the exponents, you add 3 to it. So that way you will figure out what you need to store in the 3 bits that you have in here. Then here you store the sign and whatever the fraction you have in there. That's it, period. Okay? So this is when you need to store a number, right? That's basically what you need to do. Okay? But what if you have a stored number and then you need to convert it back? I know, like basically, right, guys, I know that this is the sign, right? And also we know that this is the saved exponent, right? We subtract 3 because we save it by adding 3. So if we subtract the added 3, then we're going to get our own numbers, right? So here, if you have 2 minus 3, you're going to get your -1 back. Okay? So this is very important to keep in mind, okay? So now we're going to do this one to get the component, the bias component, and this is going to be my fraction that I have stored in there, okay? And then this is going to be my formula. This is very important for you to remember. So we're going to use this formula to convert this number. So we're going to do some multiplication, binary multiplication. So if you forgot how to multiply binary, how to do binary multiplication, I have a reference right here, okay? So go to the spot, they will show you how to do binary multiplication. So first of all, let's look at this formula by an example right now. So now I have -1. What is the sign right here? So the sign is 0. So -1 to the power 0 multiplied by 1. That's going to be always there. What is the significant right here? Okay, so the significant fraction is going to be 0, 0, 1. So that's going to be my fraction. And this is 2 to the power what? E minus 3. So we have E, which is 2, the stored exponent, minus 3, the bias exponent. We're going to get -1. Okay, so I know that this number equal to this, but I want you to learn how to convert it. Okay, so if you do this part right here, then this is -1 to the power 0 is going to give you 1. And this is going to be your number, 2 to the power negative 1. So this is going to be what? It's going to be half, right? So this is going to be half. This is how we write a half in binary. Okay, if you forgot that, as I said, just refer to your basics, introduction to computing. I have some slides in the upcoming topics that they have details, okay? But if you just needed it right now, you can do that by just like looking at the upcoming slides, you will see some information in there. So if you do the multiplication, if you multiply this number with this number, you should get 9.16. Do you know why? Because you have 1 point, and then you have 0, 0, 1, and you multiply this by what? 0.1, right? So if you do this multiplication, you're just going to say 1 by 1, right? So this is 0, 0, and then 1. And this is going to be what? This is going to be what? 0, 0, right, guys? You remember that? So this is the only one we have in here. And if we do this number, then now we're just going to do the basic multiplication. If you do this basic multiplication right here, you should get this number, right? Okay? So, but why this number? Why the floating point decided to be here? So how many digits you have in here? 3, right? And how many fraction you have in here? Number of digits is 1. So 3 plus 1 is going to be what? It's going to be 4. So that's going to decide where the floating point is going to go. So it's going to go 4 points in here. So that's why you get this number. So if you want to know what this number is 9 over 16. Over 16. How? I'll show you a very simple trick. I'll explain that in more details. But what's 2 to the power 4? 2 to the power 4, 16. So that's going to go to the denominator. Okay, what is this number in binary? This is 1, 2, 4, 8. So this is 9. So I know 9 by 16. So that's going to be 5625. Okay, so these are little details, but they are very important. So if you look at this number, now I know what this number is. This number is either this or it's going to be 9 by 16. For you, if you get it 9 by 16, is easy. Number of digits, 2 to the number of digits, 2, 4 is going to be 16. And the denominator is going to be just whatever the binary number, which is 9. If you get that one, that's okay. You don't need a calculator. Okay? So this is basically what the big picture is. And then now we're going to look into the real floating point in x86. But before we go there, as I said, if you have a CPU and the CPU is divided into integers and floating point, then we need to know that how the CPU, when we fetch, decode, and execute, how the CPU is going to really recognize that this instruction is add and for floating point or add for integer points. So the whole idea right here, the instructions are already being, the operation code, you know what I mean by the operation code, right? So the operation code already have a specific bit that if the CPU find this specific bit is on, it knows that the bit is set. That means this is a what? This is a floating point instruction. And as you can see later, we actually denote them by fadd. So this is add, floating point fadd. This is mul, floating point or imul, floating point we just say fmul. Okay, so this donation or this, the way we distinguish floating from integer operation or instruction is already taken care of by the operation code. So the operation code is going to tell the CPU. Okay, so this is what is in the book. This is the real binary representation. So instead of a byte, which is unrealistic, but hopefully now you know the whole idea because byte is small and we learn what it takes, but it's the same in here. We have 1 bit for the sign and we have a specific number of bits for the exponent, right? Instead of 3 right here, we're going to have a different exponent right there. We might have 8-bit, okay? And then we're going to have the fractions right there. So this is the IEEE. There are a variety of ways, guys, to represent floating point numbers. So that's why we are going to follow the IEEE formatting. So if you find a different format, that's okay. That's not the only format, but IEEE is well known. Okay, so if you look at the IEEE, this is what I'm following in this class. So this is what IEEE is all about. So it's going to have 1 bit. You have 32 bits right here, okay, 4 bytes. And then you're going to take the first sign, the first bit for the sign, 8 bits for the exponents, and 23 bits for what? for the fraction. That's really great. If you want to do double, this is the single. This is when you say float in Java or in C, I'm sorry. Okay, and this is the double. Okay, when you say double precision, then you have 1 bit for the sign, but you have 11 for the exponent. Okay, and we're going to see if you say the exponent, what is the bias exponent? And the 8-bit is going to be 3. So what is the maximum of this? Because you have positive and negative, right? We have to consider positive and negative because it's not an integer in here. It's not an unsigned. Things could be positive or negative, right? So we have to think about that as well. And you also can think of that as also double extended precision. So this is really crazy. You have 16-bit for the exponent, and you have 63 bits for the fractional, okay, or for the fraction part. So this is very interesting. So it's gonna always be about the exponents. It's the precision and the accuracy. You might feel like, why it's only 11 here and 52 in there? Why is more to the fraction? That depends mainly on the precision and the accuracy. Okay, so this is a decision that they have already made before. So this is mainly, if we look at this part, this is nothing new. The only thing new here is we are not adding 3 now. We are adding what? 127. Why 127? Because that's your maximum number. You're going to go from negative 126 to positive 127. If that's your maximum, then this is going to be your bias exponent. When we have 8-bit, it was what? Negative 2 to 3. So we chosen 3 as our main exponent. Why? If I add 3 to 3, I'm going to get 6. So I know that if something beyond 6, 7, or 8, then I know if either it's infinity or it's going to be not a number, because these are the only other 2 codes. The same applies right here. Okay? So this is what I was talking about. That's your range right here. And I'm going to talk about this in more details in the next class. So for now, I just want you to keep in mind that storing floating point numbers are very important in terms of binary, and we're going to cover this in the upcoming class. We're going to continue that, and hopefully we're going to also cover how to do basic arithmetic, okay? So I can see like my office hours will start in just 5 minutes, so I have to stop right here, and we're going to continue on Wednesday, all right? So bye for now. Thank you, guys.